In this section, we are going to talk about the different types of stresses and how to process them. What are the different classifications of stresses found in the international codes and how they are related to the level of modeling and what sort of procedures and factors apply to those stresses to be able to perform a proper fatigue check. In the beginning, I will talk about stresses in general. You extract from your model 4 types of stresses: axial, bending, shear, and torsion. You will end up having a scatter group of stresses. To be able to use those stresses for fatigue check, you need to process them. First, you need to calculate the principal stresses using Morse circle, especially if you have a non-symmetrical section. And then you combine those stresses using von Mises, which is the most common rule for combination for steel structures. Basically, you check fatigue against combined stresses rather than individual stresses, and then you check fatigue against shear as an independent separate check alongside with the combined stresses check. We understood how to process stresses extracted from the analysis model. Now we are going to explain how codes and standards identify fatigue stresses and relate them to different modeling levels. We have 3 categories of fatigue stresses at 3 different modeling levels. Nominal stresses at the global level, modified nominal stresses at macro level, and then geometrical stresses at micro level. Nominal stresses where you have your stress trajectories, the continuous, and stress flow is laminar. Example for that, plain steel elements. Modified nominal stresses where you have macro geometrical parameter cause discontinuity in the stress trajectories leads to a stress concentration, which increases the nominal stresses. Examples for that next to bolt holes and artery entrant corners. And we can notice the stress concentration around the hole and the stress concentration around the re-entrant corners. Finally, geometrical stresses at hot spots. In the beginning, I would like to explain that codes refer to the stresses at weld toes here as the stresses at hot spots. This is a zone of a high stress concentration due to the microgeometry of the weld and the notch effect created by the weld in the parent metal. Let's talk about each one of them in a bit more detail. Nominal stresses are the stresses that you get straight away from your model without any playing around, and it's calculated based on the elastic theory. In some situation, you would need to do some tweaking to the nominal stresses due to modeling assumption or compatibility phenomena that causes increases in the sectional stresses. I will talk first about tweaking required to account for modeling assumptions. The obvious example for that is the lattice girder composed of hollow structural section. The intersection of the structural element forms a stiff zone that creates a bit of rigidity, results in a secondary fixity moment arise alongside with the axial force within the structural elements. If you decided to model the intersection as pinned, in that case you are neglecting the effect of secondary moment. Here, Australian code and Eurocode provide tabulated value for a correction factor that correct the nominal stresses to account for the secondary moment. But if you decided to model the intersection as rigid connection, in that case, you don't need any sort of correction, and stresses coming out of your model already consider the effect of secondary moment. Now I will talk about tweaks required because of compatibility issue. And the obvious example for that is the shear lag in a box girder. If you decided to use the gross properties to calculate the stress distribution across a section, you will end up having the well-known linear stress distribution. But because of the shear lag, the stresses are a bit higher than what is being calculated based on the gross inertia. To capture that, you need to use the effective properties of area. As we can see, stress distribution with shear lag is different than the stress distribution without shear lag. Nominal stresses will equal to the stress distribution with shear lag, which is a bit higher than the other one. For the modified nominal stresses, to capture the stress concentration, we need to calculate the stress concentration factor. Normally, for macro level analysis, there are tabulated values, formulas, or charts to estimate the stress concentration factor, or you can use the finite element modeling. However, this is not a common method to calculate the stress concentration factor, especially at the level of analysis, the macro level. Examples for a situation where you can use tabulated values or formula to calculate the stress concentration factors is at door hatches and lightning pool, or the stress concentration that arises from a misalignment between two welded plates. Or you can use charts, as we can see here in case of holes or re-entrant corners, where you can get the stress concentration factor based on the hole size and its location from the edge of the plate, or you can get your stress concentration factor based on the geometry of the re-entrant corner from these charts. You can use the stress concentration factor to increase the demand, or in some codes, you can use the stress concentration factor and the strength side to decrease the strength. In either cases, strength has to be bigger than the demand. Now for the geometrical stresses at hotspot, again, you still need to capture the stress concentration at well toes or hotspot as they are being called in the codes and standards. You still need to calculate the stress concentration factors. There are several methods to do that, but before dwelling into this, we need to clarify something first. Codes and standards provide the designer with a value for the fatigue strength. This value is based on testing for a range of plate thicknesses and member sizes. Hence, your connection might fit within the testing range conducted by the code, or it could fall out of that range. With this in mind, let's talk about the methods of calculating the stress concentration factors at hotspots or well toes. Let's start with the no button, where your connection your connection fits within the testing range conducted by the code. In that case, the stress concentration at well toes are already inherited, and the fatigue strength given by the code are inherited in the fatigue strength given by the code. And you do not need to do any sort of calculation to get the stress concentration factor. But unfortunately, in that case, the given fatigue strength values are conservative. That's why codes provide alternative method to calculate the stress concentration factor with more refined analysis, which moves us to the next button. You could use a parametric formula to calculate the stress concentration factor. Your connection still fits within the testing range conducted by the code, so you can use a parametric formula to calculate the stress concentration factor. Australian code and Eurocode refers you to some reference books for that purpose. However, the American code has formulas in it for that stress concentration factor. Because you are putting in an extra effort and doing more refined analysis to calculate the stress concentration factor, the code sort of rewards you for doing this, and that by providing higher fatigue strength rather than the conservative one explained in the no button. And then it's up to you to build a finite element model in case you want to verify the stress concentration factor calculated by the formula against the finite element model. or you can opt for not doing that as it's not necessarily required. Finally, let's talk about the finite element modeling to calculate the stress concentration factor. And you resort to this when your connection does not fit within the testing range conducted by the code. In that case, doing finite element modeling is mandatory. And again, because you are doing refined analysis to calculate the stress concentration factor, you are still eligible to use the higher fatigue strength provided by the code when you're doing such a thing rather than the conservative value.